Now that we are experts at understanding exponential growth and decay and how to identify which kind it is by looking at the b-value and going from the equation to the table of values to the graph and doing our tests to prove that it's exponential, let's take a look at a number of application problems together. So I did not make these notes. I'm working through notes from another teacher here. So there might be a little bit of overlap, things we've already talked about, or a couple things that we don't strictly need to know for this course, but I'll highlight those points when we get there. So let's start with a quick overview first. So we're going to be modeling exponential growth. So we're using our equation as a model to describe something that's happening in real life, and then using it to predict things like what will the population be after a certain amount of time. And generally our formula for exponential growth is y equals a times b to the power of t. We usually use x, but often it represents time, so t for time here, that's fine. It doesn't matter what letter we use for variables. I could use q, I could use z, it really doesn't matter. It's just kind of convention that we normally use x or sometimes switch to t when we're trying to describe time specifically. So let's talk just generally about exponential equations for a moment. I know that my a value is my starting amount. I know that on my graph it is my y-intercept. So it is where my curve crosses or touches the y-axis. And I know that it's the y value when x or t equals 0. Or t equals 0. I know that b, if b is greater than 1, so as an example, like 1.1, 1.2, 3, etc. When b is greater than 1, we have growth. And in that case, b equals 1 plus the growth rate. So if I'm doubling every time, doubling is the same as adding an extra 100% each time. So if my b is 2 because it doubles, that's equal to 1. So 100% original plus 100% new growth. And this sheet specifically talks about growth, but let's talk about decay right away as well as a continuation from our last video. If b is between 0 and 1, and I'm going to use the mathematical way of writing it right now just to save space on the page, but just know that this part means b is between 0 and 1. So as an example, we would have values like half or 0.6 or 0.85. It can't be 0 because if we're multiplying by 0, my graph just goes to 0 and it's always 0. And it can't be 1 because if my b value is 1 and this is my a value, my graph just never changes. I'm just multiplying a by 1 over and over and over again. Multiplying by 1, we're just stuck at the original value. Nothing changes. So it can't be 1 and it can't be 0, but it can be any number in between. And in this case, I have decay. And then in this case, my b value is equal to 1 minus my decay rate. So if my car loses 10% of its value every year, b is going to be 1, represents 100% of my current value, minus 10% that I lose every year. So 1 minus, convert that percentage into a decimal. My b would be 90. So basically what that means is my car keeps 90% of its value each year, or in other words, my car loses 10% of its value each year, whatever way you want to think about it or describe it. I'm going to erase that just to keep my note neat, but you may want to write that part down in your own notes. As always, your notes are your notes. Imagine you're writing a message to your future self. What is your future self going to need to know? What are the things that you find challenging now that you might forget in the future? What are the tips and tricks or the ways of thinking about it right now that are helping you to understand? Make that note so your future self can look back on it and thank you, rather than your future self looking back and seeing like, this is just Mr. Strike's notes. This didn't make sense the first time. I just copied it down. That doesn't help. Write something that will help you. All right, let's do some application problems together. As previously mentioned, one of the most common things we do with exponential growth is to talk about populations of living things, often bacteria, and that is the case here. So let's read through our first question and let's discuss and solve it together. Question 1. A bacteria population can be modeled by the equation P equals 150 times 2 to the power of t, where t is the number of days. What is the initial population of bacteria? We don't even have to do any calculations here. And in fact, as we work through this stuff, I would encourage you to pause and try to answer these on your own before you watch me write the answer out, just to test yourself and just to help your brain develop those connections. So try it on your own. Think, what did Mr. Strike say about initial value before? There's three numbers here or whatever. There's the A value, the B value, and then the T or the X. What do those stand for? Do I already know what the initial value is? Maybe you do. So I would encourage you to pause and try that on your own first. Just scribble it down on a piece of paper. Or if you're doing this during class, there is a copy of this posted to Classroom. Whatever way works best for you. Now, assuming that you've paused and tried this on your own, let's go ahead and answer these questions. What is the initial population of bacteria? Well, the A value here represents starting value or initial amount every time. I see that my A value is equal to 150. And this is a word problem, so we'll say therefore initial population of bacteria is 150. Or you could write that in your own words and you could say something like, when we start measuring, there are 150 bacteria present. Next question, what is the population of bacteria after 8 days? So which part of our equation are we going to change? Do I know the p-value? No, that's what I'm trying to find out. What is the population? So I want to figure out the p. And I know the relationship between p and t. So 150 times 2 to the power of t. And I know my t value. 8 days means 8 days have passed. T is my number of days. So t is equal to 8. So all I need to do is, we call this evaluating our function or evaluating our equation. We just take a value for t or x or whatever we called our variable and we plug it into our equation. So I know the value that's going to go into my machine and I want to calculate the value that's coming out. And in this case, we're calling our input value t because my input represents time. So let's plug that into our equation. So population is going to be starting with 150. 2 means we're doubling every day. And number of days is 8. Once again, as you put this into your calculator, this part has to come first. Start with 2 to the power of 8, then multiply by 150. If you're doing it in the wrong order, if you are not following the rules for order of operations, you are going to get the wrong answer. So please be careful as you do that. And let's calculate. We're going to have 2 to the power of 8 is 256 times 150 is, and this is a pretty big number, but that's the power of exponential growth. Things grow, the numbers get big really quickly. Population is 38,400. Therefore, after 8 days, there are 38,400 bacteria. And I will make a quick note. Technically, see how I'm drawing the comma here? Technically, in North America, that's not the proper format, but it makes life a lot easier when we can group things by the thousands. So I'm going to do it anyway because it makes my life a lot easier, and I think it will make your life a lot easier, but you may have teachers in the future or something that discourage you from doing that. Now, this last part, we do not need to learn this skill in this course. I'm going to show it to you anyway, but it is not required. So if you find this part confusing, don't worry about it. You can straight up fast forward and skip this if you're already confused. But I still want to show you that it's possible, and so I'll do a quick overview of what we're doing here. All right, let's take a look at what we're solving here. For question C, it says, how many days does it take for the bacteria population to reach 153,600? In this case, we know our population, 153,600. I know my equation, 150 times 2 to the power of t, and I don't know my time. So what I could do is I could write out part of my equation. So I can start 153, 6,000 is my population. I have the same starting amount. I have the same b value. I just need to figure out that t value. And so I can start solving using the skills I've learned before. Right now I have 150 multiplying by this. So I can divide each side of my equation by 150. So remember, whatever we do to one side, we do to the other. And so I can simplify this a little bit. 153, 600 divided by 150 is 1024 equals 2 to the power of t. And that looks pretty reasonable. But now, how do I solve for t? How do I solve for an exponent? So we've been talking about exponential equations. And it turns out I need to like undo my exponent. I need to cancel out the operation of, sorry, it looks like my video isn't keeping up. I just need to pause for a moment here. Sorry if the video got choppy there for a moment. I just saw the warning message and I don't know how long it was on the screen. So I'm not going to fix this. Sometimes I leave my mistakes in on purpose. So you can see that your teachers make mistakes too, either on the technology side or the math solving side. But then I like to show you how to recover from it too, as applicable. So we're not going to, hopefully it's okay. We're just going to keep going. So I have 1024 equals 2 to the power of t. I somehow need to undo that exponent operation. I need to do the opposite of exponential. And the opposite of exponential is called the logarithm. This is not part of our curriculum. It is not necessary. There are other ways of solving this. I could guess and check. So in my calculator, I could just start guessing numbers, 2 to the power of 1, 2 to the power of 3, 2 to the power of 6. And I could try to guess a number that makes this equation 2 to the power of what equals 1024. And that's a pretty straightforward number. I could probably figure it out. So logarithm was the first method. Or we can use guess and check. But I hate guess and check. It has its place. It is a useful tool to use sometimes in our math toolbox. But frankly, I just don't want to have to ask you these questions. I'm still going to go through it, though, and show you. So we could guess and check our numbers until we find a t value that allows this to be true, or we can solve it using an algorithm. And basically what we're going to do, and once again, I just want to show you that this is possible. We're going to take the logarithm of each side of the equation. So we're going to take logarithm base 2 of this side of the equation and logarithm base 2 of this side of the equation. So really, what am I going to do on my calculator? It's going to look like this. T is going to equal logarithm 1024 divided by logarithm 2. So I'm rearranging this equation. I'm undoing the exponent. So basically this part and this part cancel out, and I'm just left with the t. And this part right here equals this part right here. And I'm not going to go into the details of how that works. If you want to observe and see the pattern and see, oh, I get that. I know there's a log button on my calculator, so I just gotta put this number in here and this number in here, and I can solve. If you get it and you want to use this tool, that is great. However, I'm generally going to avoid asking you these questions just because it's not strictly part of the course, and I just want to focus on the essentials of our course material. I do still want you to see that it's possible and that there are mathematical tools to solve this, though. So as I solve this into my calculator, I type log 1024 divided by log 2, and I get an answer of 10. And therefore, population is 153,600 after 10 days. So if this was confusing, don't worry about it. Just skip ahead. But if you want to take a moment and look through and see, oh, there is a tool for solving this, this is what it looks like, you're welcome to do so. And we are going to have another question related to this, just because, once again, I'm using another teacher's material, and it doesn't hurt to know what's possible, but I'm not going to quiz you on using logarithms specifically. All right, let's move on. Let's get back into some more familiar territory, and let's take a look at a financial application question. How can I use exponential growth to learn about finances or to describe financial situations? We are told that Pam invests a sum of money into an account that earns 5% per year. The amount of money in Pam's account is modeled by the equation A, so that's the amount in the account, equals 2,500 times 1.05 to the power of t, where t is the number of years. And once again, I would encourage you to pause and try this before following along. So assuming you've already done that, let's keep going. We know my exponential equation is always in the form y equals a b to the x. A is my starting amount, and here my a value is 2,500. So our first question, how much money did Pam originally invest in the account? Therefore, Pam started with $2,500. Before we move on, let's also talk about our B value. It's not really part of the question. This is our first time doing application questions, so let's take a moment. My B value is bigger than 1, so it's going to be growth. So I know that B equals 1 plus the growth rate. I know B is 1.05. And so I'm going to subtract 1 from each side. And I'm going to find out that 0.5 equals my growth rate. Or when we talk about our money growing, we call it our interest rate. And that's actually given in the question. It says it earns 5% interest per year. And so 5% becomes our growth rate, just like we've talked about before. So just a quick aside to describe how the interest rate applies to our exponential growth equation. And we'll talk about that more and look into some other related situations when we dive into our financial unit. So for the sake of keeping the note clean, I'm going to erase some of this, but I'll still mention the B value off to the side there. Next question. How much money will Pam have in 30 years? Once again, we know the equation. The amount in the account is given by the equation A equals 2,500 times 1.05 to the power of t. We know that the amount of time that's passed is 30 years. And make sure it's the same. T is number of years. One of these could have been given in months, and then we'd have to convert. So just be careful and make sure they're using the same unit. And I don't know what the new amount is. I'm going to find out. So I'm going to evaluate the function. That means I'm going to take my t value and plug it into my equation and solve for my a value. So what's the amount going to be? Well, let's find out. We started with 2,500. We multiplied by 1.05 a bunch of times. So that means we kept our original money. That's what the 1 represents. 100% of the original money plus an extra 5%. And we did that 30 times. So we earned a new 5% every year over 30 years. So the amount of money in the account is going to be 2,500 times 1.05 to the power of 30. As always, if you're using your calculator or doing it by hand or whatever, this part first, deal with the exponent first, then multiply your answer by the a value. It is vital that you do that in order. Otherwise, you're going to have it set up all correctly, and then you're going to get the wrong answer, and none of us want that. Our answer is going to be 10,804 and 86 cents. So therefore, after 30 years, she will have $10,804.86. And once again, we see that compound interest, which is what this is an example of, and we'll talk about that more later on. Compound interest, or just in general, exponential growth is really powerful. We can start with a relatively small amount of money, and even if there's a relatively low interest rate, although 5% is not a terrible rate of return on something, we end up with a lot of money by just letting it sit there over time. So exponential growth can be really helpful. Now, once again, question C asks us to work backwards. We're going to use a logarithm, so you do not have to know how to do this. If you found it confusing in question 1, or if you skipped it, you do not have to watch this, but I do want to demonstrate to you that it is possible and what it looks like. So in this case, we know our amount. It says that how many years does it take for the investment to reach $8,062.75. So I know the amount. I know the equation. The equation doesn't change. 2,500 times 1.05 to the power of t. And I want to figure out my t value this time. So let's write out our equation with the numbers that we know. A is 8,062.75 equals 2,500 times 1.05 to the power of t. I can start to simplify using tools I'm familiar with. So right now I'm multiplying 2,500 times this term. So I'm going to divide each side by 2,500. And I'm going to get 8,062.75 divided by 2,500 is 3.2251 equals 1.05 to the power of t. Now I'm going to use my logarithm. I'm going to rearrange this, and I'm going to find that t is equal to logarithm 3.2251 divided by logarithm 1.05. So this number is going on top. This number is going on the bottom. And let's plug this in our calculator and solve. So log 3.2251 divided by log 1.05 gives us 24.000000. So we can pretty confidently say it's 24. Therefore, it takes 24 years to earn that amount. And once again, you do not need to know how to do this. I want you to see that it's possible, but if it's confusing, just skip it and move on. Next up, let's take a look at some questions that specifically focus on exponential decay. As a quick reminder, what is our graph of exponential growth going to look like? Well, it's going to curve up, starting at our a value. So this is my a value that represents our y-intercept. And exponential growth starts high and goes low. So once again, I start at my a value, and I'm going to curve down. The fun thing about exponential decay is that it's never actually going to reach zero. We're always just multiplying by some number. And I can't multiply some number enough times or divide a number enough times for it to reach zero. So it'll get really, really close. I mean, eventually it'll be less than 1 cent. So we would just round down. Or in terms of radioactive decay, eventually the number of grams of material we have left is like less than the weight of an atom. So in terms of physical limitations, I mean, you can't cut an atom into 1,000,000 pieces. Technically you kind of can, but we'll ignore that. But there's a limit. It won't actually reach zero. It'll just get really, really close. All right, let's take a look at some examples. Question 1. The amount of plutonium in grams is modeled by A equals 250 times half to the power of T. What that means is we're going to start with 250 grams. My B value is between 0 and 1, so it's decay, and it's actually going to be cut in half every time. So we're dividing by 2, or we're multiplying by 50% every time to find our next number, and T is my number of years. So first question, what is the initial amount of plutonium? That's my A value, which is 250. So therefore, initial amount of, and our symbol for plutonium is just P. Oh, sorry, Pu, not P. Initial amount of plutonium is 250. And don't forget the units. It says the amount is in grams. So 250 grams. Next question. How many grams of plutonium remain after 5 years? Well, I'm going to figure out the amount. I have the equation. And I'm not showing as much work this time just because I already did that in my previous questions earlier in the video. So I'm just going to write out my equation. I'm going to evaluate my equation for when t is equal to 5 years. And notice the units are the same, years and years. That's good. So I'm just going to plug in a 5, and I'm going to type this in my calculator. Remember, once again, and I keep saying this every time because it's super important and a super common mistake, deal with the base and the exponent first, then multiply by the 250. You can probably just type it all in your calculator and it will be fine. But if you're getting weird answers, or if you want to do it a piece at a time, deal with that part first. So on my calculator, I'm going to do 0.5 to the power of 5 times 250. And I'm going to round my answer, but it's going to be basically 7.81. Therefore, we need our concluding statement because it's a word problem. After 5 years, there are 7.81 grams of plutonium. Question C is once again one of those questions that wants us to work backwards and find the time. So I will demonstrate that to you quickly. I know the amount is going to be 1.95 grams equals my equation, 250 starting amount, gets cut in half every time to the power of t. In order to start rearranging my equation, I'm going to divide each side by 250, which is going to give me 1.95 over 250, 0.0078. equals half to the power of t, and I'm going to do my logarithm. T equals log of the number on the left, 0.0078. And you do have a log button on your calculator, so you can do this calculation if you wish. I'm actually going to convert that to a decimal just to be consistent, but it doesn't really matter. All right, and t is going to equal, let's find out. So logarithm of answer divided by logarithm 0.5. T is going to equal about 7. Therefore, and I'm just going to write a really short concluding statement because I don't want to spend too much time on these questions. Therefore, it will take t equals 7, and t is number of years, so it will take 7 years. So we have a problem related to radioactive decay. We're also going to take a look at depreciation. So the value of a used car can be modeled by V for value equals 6,300 times 0.85 to the power of t, where t is the number of years. What was the original price of the car? Original price is our initial or starting value. That's my A value. So therefore, original price was $6,300. What is the value of the used car after 3 years? That's going to be my t value. So I'm going to evaluate my function when t is equal to 3. And I'm showing less work now because I've shown you a lot of details in the previous questions, so we can start to work a little bit faster. And we're going to have 6,300 times 0.85 to the power of 3. And that's going to give us a value of 3868.99. So therefore, after 3 years, the value is $3,868.99. Once again, our last question asks us to work backwards. I'm still going to demonstrate that for you. 1240 is the value, equals 6,300 times 0.85 to the power of 3. And I'm going to skip even another step. Oops, not to the power of 3, to the power of t. And I'm going to skip even another step this time and go straight to my final calculation. I'm following the same process as before. I'm just showing less work, so you can check that out if you want. But basically, we're going to have t is equal to logarithm 1240 divided by 6,300 over logarithm 0.85. And I'm just basically skipping steps and putting everything all into one calculation. So on my calculator, I'm going to do log 1240 over 6,300 divided by log 0.85, and that's going to give me a value of 10. So therefore, it will take 10 years to have that value. Finally, let's take a look at a couple extra financial questions, just because I want to try to include a few extra financial examples for you. Many of you were interested in it, and we're going to need these skills in our upcoming lessons on finance. So if we can get a foundation and at least a little bit of familiarity with these ideas and these types of questions, we'll be more prepared for our future questions. So 2 final questions to wrap up this video on this handout. Number 1, Ricky invested $1,200 into an account that earned 5% interest per year. How much money will Ricky have in 20 years? And notice this time, we don't have the equation. So let's start by figuring out the equation. I know that from my exponential, they always look like this. Y equals AB to the X. A is my starting amount. What is my A value? And I would encourage you to pause and try to answer this on your own before you follow along with me. So assuming you've already done that, let's continue. A is going to be my starting amount. We start with $1,200. B, this is going to be growth because we're earning money. So B is going to be 1 plus the growth rate. Or when we're dealing with money, growth rate is often our interest rate. And then we're told here our interest rate is 5% per year. And everything's measured in years, so there's no conversion. We can just plug the numbers straight in. So B is going to be 1 plus 5%. Or in other words, B is going to be 1 plus, convert our percentage to a decimal. That's why we started building that skill last week already. 5% becomes 0.05. Or basically I take 5 and divide by 100. And then I just add my numbers together. And there's my B value. And what does T equal? Or what does our x value equal? Well, we're actually told, and it's part of the question, we know that it has a value of 20. So let's just say t equals 20, or x. It doesn't matter what we call it. So our new equation here for our amount of money in the bank is going to be A is 1200, B is 1.05, and T is our amount of time. And we know that T equals 20, so A equals, so we're going to evaluate for T equals 20. $1,200, increasing by 5% each year, 20 times over. It's going to give us a value of 1,200 times 1.05 to the power of 20 is $3,183.96. So therefore, in 20 years, Ricky will have $3,183.96. Looking good. If you have any questions about that, pop into our Google Meet or email me and I can answer them for you. Final question here to wrap up our assignment, or our note. Amy invests $1,000 in an account that pays 4.5% interest. Bob invests $2,000 in an account that pays 2% interest. After 40 years, who will have more money in their account? And so this is asking us to compare. So we have to do two questions here and see who made the most money. So I'm going to divide my area on my paper into columns. I'm going to have Amy, and I'm going to have Bob, and I'm going to use the same color pen still because it's annoying to switch back and forth. And let's find the equations that describe their amount of money. I'm going to show a little bit less work again this time because I already showed all my steps the first time, but I'll still talk it through with you. The amount of money that Amy is going to earn, we'll represent that with A, and her starting amount is going to be $1,000. Her interest rate is 4.5%, so 1 plus the growth rate, 1 plus 4.5% is 0.45, so 1.045 to the power of t. That is our time that has passed in years. We'll use B for Bob on this side, and he started with $2,000. And his interest rate was 2%, so 1 plus 2% is 1.02 to the power of t. And in each case, we're seeing what happened after 40 years. So we're going to evaluate each function. We're going to plug t equals 40 into each equation, and let's see what we get. A is equal to 1,000 times 1.045 to the power of 40. And so Amy is going to have $5,816.36 in her account. Bob is going to have 2,000 times 1.02 to the power of t equals 40. So to the power of 40, and let's calculate. 2,000, 1.02 to the power of 40. And Bob is going to have $4,416.08. So even though Bob started with more money to begin with, 2,000 versus 1,000, the growth rate, the interest rate made a big difference. And once again, that's the power of compound interest. That is the power of exponential growth. Even if you start with a little bit less, if the percentage is bigger, you're going to earn more and more money each year and eventually catch up and surpass Bob. Let's actually switch to Desmos for a quick second and just see what these look like as a graph. So we can answer all these great application questions without graphs, but graphing can be useful. It helps us visualize and see what's going on. We can quickly see trends. So let's take a quick peek, and then we'll come back and wrap up this question. All right, so we're taking a look at our screen in Desmos. I've already put in my equations for Amy and Bob, and now I just need to turn them on. So let's take a look at the curve for Amy's money. She started with $1,000, and this is increasing at that rate of 4.5% per year, and we see the years along the bottom. And let's just confirm what happens when we're at 40 years. We're going to have just about $5,820, which is just about what we expected. And with Bob, we can see that Bob started with more money, $2,000, but notice that the curve is less steep, and that's because his growth rate, or his interest rate, was only 2% versus 4.5% for Amy. And let's just confirm, after 40 years, he should have about $4,400, and he has about $4,400. That looks great. That's exactly the number we calculated. And the point here is I won't ask you to answer questions like this, but just know that it's possible. we can see at a specific point. Sorry, I think part of what I just showed you was cut off on the screen. There we go. There we go. Now we can see the whole thing. Anyway, the point is, at some point, it becomes not worth it. So Bob started with more money, but he earns less money. So he's ahead for the first 5, 10, 15, 20, 25 years. But at year 28 and a half, they cross over. So if the investment's going to be for longer than 28.6 years, it makes sense to go with Amy's. Amy ends up with more money. And look how more quickly it's growing now. You end up with a big difference between these two curves, a big difference in the amount of money if enough time is allowed to pass. So in different courses, we would maybe take the time to investigate this. For now, I just want to point out that it's possible and that we could answer an application question about this by saying that Bob has the better deal for the first 28.6 years. He has more money in his account, but after that point, Amy's value becomes higher. So if the investment is for more than 28 and a half years, then Amy's going to make more money and Amy is the way to go. And we specifically looked at 40 years, and 40 is definitely more than 28.6. So let's jump back to our handout and let's finish answering that question. All right, so the question said, after 40 years, who will have more money in their account? Well, we've seen visually on the graph and through our calculation that the amount of money Amy has is greater than the amount of money that Bob has. So let's just write a concluding statement and then we'll be done. Therefore, Amy will have more money in the account, in her account, after 40 years, and technically after 28.6 years, but we don't actually have enough information from our calculations here to prove that. So hopefully that was helpful. Hopefully you've gotten a feel for what kind of application questions will be asked when dealing with exponential growth, exponential decay, or finances. Hopefully you're okay with the calculations. I tried to break it down into as many clear steps as possible, but if you do still have questions, please let me know and I would be happy to answer them.